Okay, so if you remember, we were discussing the forces and the torque acting on magnetic dipoles. Today, I would like to first go back to one of our previous systems that we had qualitatively discussed, the one-Allen belts. If you remember, we said that if we have the Earth is basically a magnet, a huge one. So if you consider the magnetic field lines, there are all these charged particles coming from the sun. And when they arrive close to Earth, they basically make helices around these magnetic field lines of Earth. And when they come to approach the poles, where these magnetic field lines, the B field lines kind of converge, there will be a force in the other direction to reverse the motion. So we didn't really prove that there will be such a force. Now today we can discuss that force. That is one thing I would like to discuss. And the two other things is, okay, we already derived that the force acting on a dipole is equal to the gradient of magnetic dipole moment times the scalar product, the B field, and the torque was given by M cross B for a general current distribution. Well, there's all this technical derivations in there, so kind of what the phenomena that's really going on there, kind of it's hard to see. So we will just look at some basic systems that we had also studied in the first year, just to refresh our minds. So what's actually going on, what is creating this force, what is creating this torque, how they are created. So that's what I'm planning to discuss today. Now, do you have any questions before we continue? Okay, so let's start with this force. Well, let us look at one more thing before we discuss the force acting on these charged particles as they helix towards the poles. Let me assume a region of space where the magnetic field is more or less uniform. And let's say that I have a positively charged particle which at a given instant, it moves in that direction. So what will be the direction of the force acting on this object? Downward. Why? Into the screen? Upwards. Downward. Yes, it's a positively charged. It's V cross B. Remember, the magnetic force is QV cross B over C. So it will feel an upward force, and we said that it will do a circular motion. Now, this is not a magnetostatic system, but we can, rather than talking about the point charge, maybe we can talk about the average charge density. So we can, on the average, we might be able to treat this system as a current carrying ring. So what is the direction of the magnetic dipole moment of that ring within this approximation? Remember, the direction of the magnetic moment for a loop lying on a plane was I times A in the direction normal to the area. Normal given by the right-hand rule and the direction of the current. So it's basically out of the screen, in the opposite direction of the magnetic field. That will be what's crucial. Now let's consider a negative charge moving in this direction. So what will be the direction of the force acting on this negative charge? Downward. So it will make such a circle. What is the direction of the magnetic dipole moment of this system? Out or in? Why in? What is the direction of the average current? Counterclockwise or clockwise? Remember, note that it is a negative charge. Counterclockwise, so it's again outside. So basically, whatever the direction of whatever the charge of the object, is when it is circling around these magnetic field lines, its dipole moment will be in the opposite direction to the magnetic field. So that is the crucial thing. Now we know that the force acting on this one, on a magnetic dipole, is given by this expression. So this is gradient of minus m times b, in a crude sense of the word. So, well, I'm just doing some kind of a hand wavy. Of course, you get the angles, the exact motion will be complicated, the force will be complicated, etc. But just let's make a simple, mini simplifying assumption. We know that on the average, the direction of this m will be in the opposite direction to the b. So m dot b will be minus the product of their magnitudes. So this is minus m times gradient of b. So the direction of the force is in the opposite direction to the gradient of the magnitude of b. While gradient of a scalar function tells us in which direction that function is increasing. Do you remember? You see the u, the definition of the gradient. If you get any function, if you calculate its differential, this is the gradient of f dot dl. So df is largest if dl and delta f is in the same direction. Gradient of f is in the same direction. That is, if we choose the L in the direction of gradient of f, then the increase in f is maximum. So basically that tells us that the gradient of f is the direction in which our function is increasing fastest. So if you go back here, so the force, the gradient of b is in the direction in which the magnitude of b is increasing. But the force is in the opposite direction. So the force will be in the direction, the force acting on a dipole will be in the direction in which the magnetic field is decreasing. So if you go back to this previous example, you see close to the pole, the magnetic field lines, their density is increasing, which basically means that the magnitude of the B field is increasing towards the poles, towards both of the poles, in fact. Towards both of the poles, the magnitude is increasing. If the magnitude is increasing, so the force acting on a dipole that is moving towards the poles will be away from the poles. So that's basically why this charged object, as it approaches the poles, it will feel a repulsive force, repulsive away from the poles, and it will just, eventually it will stop, and it will just bounce back, and it will move towards the other pole. And the same thing will happen again. At the other pole, as it's approaching the pole, the magnitude of the B field is increasing, so the force will be in the other direction, so it will just slow down, stop, and it will bounce back. It will just go back and forth between the two poles. And this basically follows from this law. Any questions? Okay, so let's look at our examples. let's assume we have a region where we have the some B field. And then I will assume that I have some rectangular loop inside this B field. And this is the direction of the current. So if I would just look at this loop from the side, let's say what I will see is this one. So it makes an angle. So the current is towards you at the top, and the current is into the screen at the bottom. Or if you just look at it straight up, you will see the magnetic field lines coming towards you. And it will have such a shape. Now, this is how it will appear. This is a rectangle, just a bit tilted. So this side is, let's call that side B, and the current is running in this sense. This side will also have length B, this side will have length A, this side will have length A. So we have a rectangle with sides A and B. Now, what is the direction of the force acting on this side? On the right side.
Left.
Let's see. Now, B field is towards you. Okay? So this is our rectangular loop. We are looking at this side. The current running in this side is, is moving in this sense. This is the direction of the current. The B field is towards you. And remember, the force acting on a very small segment would be I over C dl cross B. dl is in this sense, pointing up and away. B is towards you, and dl cross B is this side, out of the loop. So it will be, let me just call, yeah, okay, so let's just keep it this way, I over C times, let me call it F1. The magnitude of F1 will be equal to I over C times L times A times B at that point. Let me call this point my X, Y, and Z point. This is X, this is Y, and the Z is in your direction. So basically, the B that should appear over there is the B at the point X plus delta X. Y and Z. Some average Y value. Now, F2, the force acting on the other side, on the opposite side, what will be the direction? You see now the current is towards you and towards and below. So this is the direction of the current. B is again towards you. This is my dl, dl cross B, it is again out of my rectangle. So this is the direction of F2. And F2, let's say it is more or less I over C A times B x minus delta x, y and z. And what else do we know? B is equal to twice delta x. So I just assume that one side is at a distance delta x from the center, the other side is at a distance delta x again from the center. So the two sides, the separation between the two sides of this rectangle is twice delta x, but we said B is the length between those two sides. So B is twice delta x. So the magnitude of the horizontal force, well, the horizontal force will be due to F1 plus F2. This will be equal to I over C A times B x plus delta x y z minus B x minus delta x y z. Or if I just make a Taylor expansion around delta x is equal to 0, this will be equal to I over C A, or let me write it in this form, B of x plus delta x y z minus B of x minus delta x y z over twice delta x multiplied by twice delta x. This is equal to I over C A, well, twice delta x was what I call the B, and that difference is nothing but the derivative of the B field. And so basically, you see that this is I over C times, now I times AB is what we call the M, the magnitude of the dipole moment, times del B by del X. Of course, keep in mind that this B is actually BZ. So this is why, and M is just a constant, M over C, sorry, IAB over C is what we call M. So this is basically why we have the derivative of the B field that creates a force. So because if the B field is homogeneous, just looking at these horizontal components of this force over here, we will see that they will cancel if B field is homogeneous. The total force acting on the left-hand side will be equal to the total force acting on the right-hand side, and they will just cancel. But if the B field is not homogeneous, in that case, there will be a slight imbalance between F1 and F2, and then the net force will not be 0. So that's basically why we have in this force expression this gradient as the derivatives. Now let's look at the forces acting on the other sides. Sorry, I think I forgot one factor over here. The magnitude of F1 is not just A times B. You see, there's an angle between the two. You see, this is my DL, or DL. If you look at F1 is the DL vector is pointing away from you and upward. This is my B. So the angle between the two is not 90 degrees. So there's some angle, let's just say cosine theta. If you just look at it from the side, you see this is my side. This is the direction of M. So this is the angle between DL and B. Let me just call it phi. Now, this angle over here is theta. That is the angle between B and DL. So the force will be, the magnitude will be sine of phi but you see, if you phi plus theta is equal to pi over 2. This is perpendicular. This angle over here is theta. This angle over here is phi. So phi plus theta is pi over 2. So sine of phi is just cosine theta. This is del over del x mbz cosine theta, or del over del x m dot b. And you can basically repeat for the other components of the force if you want. So this is just one component. The horizontal component is basically the x component, and hence this is the x component of the force just turns out to be the gradient of m dot b, and we take the x component. This is the right-hand side. So we basically derive the previous result for this rectangular loop. Of course, the previous result is valid for any current density. It doesn't have to be rectangular, it doesn't have to be on a plane, etc. Now let me ask you a question. We already said that magnetic field doesn't do any work. Right? Well, if we let's go back to these charged particles. We said that there is a force acting on these charged particles, and it will reverse the direction of the velocity. So kind of, at least our description was we have this magnetic dipole on the average. This is our north pole. It's approaching the north pole, and due to this force, it will be pushed away. So isn't it doing any work? Or what is doing the work, if any? There is no electric field. There's only the magnetic field. Now, if you remember our previous example, where we had both an electric field and a magnetic field, and we were sending the the particle was initially at rest, and we said that the trajectory of this particle was this one. In that case, we said that it is the electric field that is doing the work. But here there is no electric field in this problem. So what is doing the work? Or let's say, let's look at over here. What are the forces acting on this charged particle? Yeah. It's Earth, so there's gravity plus the magnetic field. So basically, more or less the gravity, although not exactly perpendicular, but in most places, it's just like this system. You have magnetic field in some direction, which if you are close to the equator, it will be horizontal to the Earth's surface. And there is a gravity which is pulling it in perpendicular to the magnetic field lines. Well, this system, the basic idea still remains, even if the magnetic electric field is not perpendicular to it. So it's the electric field in this example that does the work, and the magnetic field just changes the direction. In the other case, it's the gravity that is doing the work, kind of is trying to accelerate the particle towards itself, but the magnetic field is just rotating the velocity in the other direction. And hence the particle just moves towards the poles, and as it's approaching the poles, again the gravity is trying to accelerate it towards the poles, but then still the magnetic field will just flip the direction. So again, it's the gravity that's doing the work in that case. Now let's look at the torque. I mean, for the torque, let's just assume B is uniform, just a simpler system. For this exactly the same system. So if B is uniform, you see, if you assume B is uniform, in that case we know that there is zero force acting on our dipole, magnetic dipole. So we have to go to the next iteration in a sense. So just think of it as a Taylor expansion in magnetic field. The first term assumes that B is uniform, constant. The second term will be proportional to the derivatives of the B fields. Now, in this Taylor expansion, the force, the contribution to the force from the homogeneous B field approximation just vanishes. So we go to the next approximation, the first variation of the B field, the derivative term. But in the case of the torque, even if the B field is homogeneous, we will see that there is a torque acting on it. So that first term will be enough. We don't need to go to the second and the third corrections to the homogeneous magnetic field. And in fact, in the case of an ideal point-like dipole, it will be only the first term that survives. So let's see, what is the... Now let's calculate the torque with respect to the center of my loop. So what is the torque? What are the torques created by these F1 and F2? Also keep in mind that F1 and F2, although I am showing them as if they are acting on a single point, that force is acting at every point along the wire. So it's made the sum of all the forces acting at every point on the wire, that F1 and F2. So what is the torque created by F1 and F2 with respect to the center of my loop? Zero, because the total force will just, since it's a uniform force, it just, in a sense, acts like gravity. So you see, when you were calculating the torque created by gravity, you always assume that the weight was passing through the center of mass. Well, basically the same idea over here. The force is uniform at every segment, so it will behave as if it is acting right at the center. But if it is acting right at the center of the segment, that means it is passing through the center of my loop. So the torque they will create, each one, will be zero. So F1 and F2 doesn't create any torque. Let's look at the forces acting on the top and the bottom segments. You see, at this point, what is the force acting at that segment of my loop? What is it there? You see, the I is pointing towards you. B is pointing towards your right. So I cross B is pointing up. So the force acting on this segment will be in this direction. This is our F3. And what about the force, total force acting over here? The current is into the screen. B field is towards your right. Downward. Well, if B is homogeneous, we know that F3 is equal to minus F4. And their magnitude will be equal to I times I over C times B times the B field, which its length is B. Now let me take this figure. So what is the torque? Remember, the torque of a force is given by R cross F. R is the position of the point at which the force is acting. So let me choose, I had already chosen this as my Z. Let's say this is X, this is Y. So what is the torque? I will just write it in two parts. It's the torque due to, let me just write it, torque due to F1, torque due to F2, torque due to F3, torque due to F4. Now, the torque due to F1 is E0. Torque due to F2, we've said that they are both 0. Now, the torque due to F3. First of all, what is the direction of the torque due to F3? How do you calculate it? Inside the screen. Inside. Okay, we have two inside votes. Come on, you basically have two choices. Inside. Let's see, you see, this is your picture. Okay, this is my current. B field is like this. Are they perpendicular? To this length. They're perpendicular. But you see, as long as one of your vectors is on your plane, the cross product containing that vector has to be perpendicular to that one. So it's perpendicular to this line, the cross product, and it's also perpendicular to this one. So it should be perpendicular to both of these vectors. So the torque will be in the plus y or minus y direction. Minus y. So this is our R vector, this is the force vector. R cross F, this is into the screen. Now, into the screen is just the minus y direction. Now, what is the magnitude? F3. Sine, what is R? Well, that side it has a length B. This side has a length B. Now, sine theta or sine phi? Which sine function? Or B over 2. So it is sine theta, sine phi, sine theta over 2, sine phi over 2. Well, let's see, it should be the angle between R and phi. Well, you see, one thing is the force. The force is perpendicular to the wire. The second thing is the angle between R and F. Oops. Now, R is in that direction. R is the position of the action point of my force relative to the origin. This is the direction of R. This is the direction of F. They're not perpendicular to each other. Or this is my R. This is my F, and the angle between the two is phi. So it's not sine theta, it is sine phi. or theta? Well, let's see. This is my phi. So this is theta, so sine theta. This is my torque due to F3, and the torque due to F4, what is its direction? The same. It's in the minus y direction. Well, its magnitude is also the same as F4. Again, sine theta times b over 2. So the total torque acting on my system is in the minus y direction. Well, F3 is m times b. No, not m, sorry. It's I times a times b. This is the magnitude of F3 times sine theta times b over 2. This is the torque due to either F3 or F4, and they are both equal to each other, so let's multiply by 2. So this is equal to minus y hat I times a times b. There's also over c. In the definition of F3, there's a 1 over c. I over c times a times the small b, the length b, times the magnitude of the b field times sine theta. This is in the minus y direction. This is nothing but my magnetic dipole moment, m or mu, magnitude of m cross b. So the torque acting on my system is m cross b, its magnitude in the minus y direction. Now, what is the direction of m cross b? Well, m cross b itself is in the minus y direction. So this is nothing but m cross b. So the torque acting on this simple loop is m cross b. It's the result that we had already derived. Any questions? Okay, so let's give a 10-minute break and we will continue afterwards.